Start. Good afternoon, everyone. My name is Anand. It's a pleasure to be here. Thanks to Dinesh for this invitation. I work in an area called complex systems, and I'm going to be spending the next maybe 30 or 40 minutes talking about not specifically the work that I have been doing, but much more trying to build an intuition for what these systems are, and the range of applications that this field has across the natural, physical, and biological sciences. So, if you look at definitions of complex systems, then you will find many. They're often described as systems built of many, a large number of components that interact together to produce emergent phenomena. Now, as a definition, it's not particularly clear what those words mean. So what I'm really going to do here is, instead of focusing on trying to define it, is to really talk through a number of systems that we call complex systems, and try to arrive at an understanding of what are the hallmarks of complex systems, what are the underlying concepts, and what it can be used to explore. I think over the last few weeks, there's been a lot of news about the weather. The cyclone which ripped through Odisha, through Bengal and onto Bangladesh. If you remember, there was about 3 weeks back, or maybe a month back, there were lots of WhatsApp messages floating around that Chennai is going to be devastated by this cyclone. But then, a few days out before the cyclone hit, it apparently changed direction, and it went into Odisha. Now, the news that's come out since then seems to suggest that the government, that the forecast was so good about the path of the cyclone that the government was able to clear out more than 1 million people out of the cyclone's way. And a similar cyclone that cost over 10,000 deaths in 1999, this time around has cost just 16 deaths. So while this speaks to a number of issues, including better preparedness in dealing with natural calamities, what it also speaks to is the challenge of modeling the weather. Now, the weather is a classic complex system. In fact, the study of complex systems and chaos began with an exploration of weather. This was way back in the 1960s, I think 61, when Edward Lorenz, a professor of atmospheric physics at MIT, he was trying to model long-term weather patterns. And what he did was he tried to develop a simple model, 10 to 12 variables, things like temperature, wind speed, etc., that he put into a basic computer that was available back then, and then let the model run over a number of time periods to try and see, what sorts of predictions can be provided for weather over long periods of time. Now, as he was running this model, one of the things that he was doing as he was testing it was to see if the model produced results that were consistent. So in one of the runs that he was doing, so he starts the model at time t is equal to 0. It runs up to some time, say 100,000 time steps, whatever it is. And then he was trying to check if the model is working properly. So what he did was to say, well, can I just use the same starting conditions and run the whole model again, and will I get the same ending conditions? So instead of running the whole model, he took some outputs from the middle. So from the previous run, he took some outputs from the middle based on the printout that he had. He input those, expecting that running the model for the same amount of time would give him the same results. But what he found was actually quite interesting, in the sense that given these inputs, the results that he got were at vast variance with what he had obtained before. Now, this is something that all of us, perhaps who work on building models, who work on thinking about how to solve problems, go through, where you sort of take something, you input it, the solution is different or doesn't make sense. We throw that, we say, there's an anomaly, move on to the next one. His genius was in saying that, well, this is actually telling me something. And what he found was interesting, was that the computer printout that he had, based on which he inputted for the second cycle, had gave him outputs at a precision of 3 digits. Now, his computer itself had a 6-digit precision. So the input that he had for the second round was only 3 digits and not 6 digits. So, but he got vastly different outcomes. And this sort of led to the first paper on chaos or even the coining of the term chaos. We basically said that systems such as the weather, which you can seemingly model with some precision, are actually are critically dependent on the initial conditions. So even very minute changes in the initial conditions can lead to dramatic changes over long periods of time, which is why weather forecasting even today is very difficult to do at 2 or 3 week time frames. So, and in December, we'll again start getting these messages on WhatsApp, etc., telling us that killer cyclone is heading to Chennai in a week's time. There is no model that can tell us this. So, from a scientific perspective, you can say that WhatsApp is crap. But, the point is that there is much greater, precision that we have 3 days out, 2 days out about what these cyclones can do, and this is what happened in Odisha is a great example. That we knew what was going to happen, we did what was required, and you really were able to minimize damage to, human life, if not property. So that's a great example of, how some of this thinking began. And this sort of dependence on initial conditions got this, in the popular culture, it's called the butterfly effect, which is, saying that if a butterfly flutters its wings in Brazil, will there be a typhoon in Texas? To say that, even small, perturbations over long periods of time can have significant impacts. And that therefore, the study of some of these systems, you have to be very mindful of, the kinds of predictions that can be made. So in any case, Lorentz's work was the beginning of an explosion of work in complex systems, the development of, work in chaos theory, and that sort of offered, a pathway to not just look at the weather, but a range of phenomenon across the natural, biological, as well as physical and social worlds. If you look at the second photo, it's a photo of a city. Now, cities have, for a long time, been thought of as systems. Cities have been thought of as organisms. These are very metaphorical descriptions of the city. So these are not precise scientific way, or these were not precise scientific ways of describing the city, but because of the way we perceive the city, it seemed like it was an organism that grew over time, that behaved in certain ways over time, or this notion of the city as a system that's composed of so many things interacting to produce the experience, the urban experience that we have. The urban theorist Jane Jacobs was the first one to call cities a problem of organized complexity. And since this description, I think it was in the 60s, there's been an explosion of work on trying to really explore cities as systems. I'm just going to sort of maybe give one example, this notion of the city as an organism. Now, one of the things that we know from the biological world is that organisms, animals, they have a certain way in which the properties of the animal change with size. It's called, scaling, where, the pace of, well, essentially, the pace of life decreases as the size of the animal increases, very, crudely speaking. That, the heart rates decrease as sizes increase. So there is a very precise, 2-3/4 scaling law, which says that, there is a nonlinear change in how the properties of, some of these organisms change with change in size. Now, what some scientists did about 10, 12 years back, 2007 to be exact, was to say, if a city is, even metaphorically called an organism, is there any way in which this can be tested? And so they took a bunch of data on a range of urban outcomes. So stuff like income growth in cities, crime in cities, infrastructure, road length in cities, a number of these things, and they said, how do these things change with city size? And they found some very interesting, outcomes. They found, for instance, that a lot of infrastructure, for instance, let's say road length in a city, it does not vary linearly with city size. It varies sublinearly. So this notion of economies of scale, that, as your city grows larger in size, you get efficiencies in the construction of infrastructure within that city. So what this, for instance, here they found the scaling with an exponent of 5 by 6. So it's less than 1, which means it's sublinear. So basically, you're using lesser, material for roads to cover the same, to cover the entire population as its income more than doubles. So what you were seeing is, that something was happening here, that there was this, that something was happening as this organism grew that was causing these kind of systematic changes in variables. And they have now found this to be true of cities across the world, with data sets, in Europe, the US, Latin American cities, China, India. So really, this seems like a scientific, or some sort of a scientific validation of the notion of the city as an organism, of the city as a system, that we can study the city and its properties using basic scientific frameworks. Now this figure, the third one, the bottom left, is what we call the evolutionary timeline. So what you have on the x-axis is time, generations. So you can think of that as millions of years. What you have on the y-axis is species. So, each dot on that represents whether a species existed, whether that particular species existed or not over time. And what you see is quite interesting, because this is, sort of an actual representation of what we know from the fossil record, is that there is a lot of consistency in, the species that exist for long periods of time. So for instance, if you look at this bit here, you have the species existing for, 20,000 odd generations. You have this species existing. And a lot of, spaces in the genotype space are not occupied. So there's a lot of consistency. But then you have this, where something is happening, and species are dramatically, coming into existence, going out of existence, before it settles into some other equilibrium. So this is sort of called a punctuated equilibrium, which is to say that there are long periods of, stability in the timeline, with short periods of, tremendous volatility. And this is sort of, this kind of intermittent behavior is sort of observed, at least in the evolutionary timeline. And a lot of the scientists who worked on, systems felt that this was rife to be explored as a complex system. So the question was, is this the observed behavior that we see in the Earth's geological record or in the Earth's fossil record? Is it just an artifact of, what has happened in Earth? Or is it something systematic about the way evolution happens, and that we should expect it in any system where evolution occurs, whether it's in Earth, some other planet, somewhere else? If there is evolution, would we find this kind of behavior? So again, what they found was interesting, and we'll sort of talk about this model in a little bit of detail later in the talk, but that this was actually an emergent phenomenon that could be derived from the interaction of individual species over time. And finally, stock markets, financial markets have been, something that, everyone here probably has a lot of knowledge about, has a lot of questions about, and has done a lot of work in. And since 2007, there's been a lot of interest in trying to understand, what happened and why did the financial markets collapse in the way that they did. There's a number of theories, there's a number of ideas about, what happened there. But one of the things that, the crash also did was to say that, are there fundamental ways in which we are misunderstanding the way we look at the system? Because if you look at this as an evolutionary system, where there are many participants, they're interacting, and they're producing all these outcomes, should we not have expected something like this? So again, this notion of the financial system as something that produces emergent outcomes from interactions of agents within the system, whether they be individual traders, banks, etc. There are so many participants, and there are so many linkages. Is there some way in which those linkages can be explored that can yield greater insight into why we see, such volatility in these systems? In 1948, Warren Weaver, who was a scientist, he sort of proposed a typology of systems, where he said that essentially, up until that point, which was, the first half of the 20th century, that science had made a lot of progress in two broad areas. One was what he called systems of simplicity. Now, these are systems that can be characterized by, 2 or 3 variables, and where the behavior of one variable can be perfectly understood by its relationship to another variable. So, Newton's laws, for instance, are a great example of this. So, the mass of a particle, the mass of an object, the acceleration that you want, then you directly compute the force that's required. And that, of course, that kind of, science led to a lot of, or led to the foundations of what we today call basic science, and to a lot of technology as well, in the 17th, 18th, and 19th century. Towards the end of the 19th century, what we also had was scientists, because of the advancements in probability theory and statistical mechanics, were finding that we could say a lot also about very big systems. So, you have those 2-body systems or 3-body systems that you could, say something about with simplicity. But here, what we found was that systems like gases, solids, liquids, which have millions and billions of particles, were now tractable, were now describable using the tools of statistics. But there are some interesting differences between the way in which we understand these systems. So if you think of, say, a billiard ball on a table, right? And you want to understand the motion of the billiard ball, just one ball on a table. Now, if there's one ball, and you know that the parameters of the table, it's fairly straightforward, given our understanding of the mechanics of motion, to predict where the ball will be at a certain point in time. The moment you add 2 or 3, the complexity rises so much. It's not that it's not doable. You have the tools to do it, but the effort required to do it becomes almost impossible. But what they found was that if you keep adding and make it 1 million balls on that table, then you really can describe that system with a great amount of precision. You still won't be able to define where an individual ball is going, but you can define the behavior of the system using, basic statistics. You can say, on average, how many balls will a given ball hit in a second? For a given length of the edge of the table, how many balls will hit it in a given period of time. So a number of these sorts of behaviors at the systemic level could be explained using statistics, without needing to know anything about, what was happening at the level of the individual ball. So the difference was that in a system of simplicity, you could track the individual particle over time and describe it very precisely. Here, given the structure of the system with almost infinite number of particles, you could track it using the tools of statistics. And I think the other important thing was that even today, a lot of our understanding of the big things in the universe, the behavior of physical systems, thermodynamics, it is all statistical. That is our understanding of it. And so in these two realms, and he called these systems of disorganized complexity. And this is critical because, it's not just that there are millions of particles here, it's that they're randomly distributed. And this is critical to using the tools of statistical mechanics. They're not ordered, and they're not moved in specific ways. They're unordered, they're moving all over the place. So this helter-skelter nature of the system is critical to its description using statistical mechanics, using probability theory. What we were suggesting was that we have made a lot of progress in these two buckets of science, and that has led to a lot of technology. I mean, a lot of what we see in the modern world is really an effect of understanding these, or really exploiting these insights. Whether it's, the way we price insurance, whether it's how modern retail works, any of these things, it's because of this fundamental notion of disorganized complexity. What he proposed was that there was a large middle area between these systems of simplicity and disorganized complexity, which he called organized complexity, that he said we have made very little progress in, that we don't understand. So this, consists of systems that, with again a large number of particles, maybe not infinite like, the disorganized case, but the most important thing was that there were interconnections between the particles. So these were not random, movements, these were not random relationships. These were systems characterized by some sort of feedback. And therefore, the randomness that was the key to using statistics goes out the window. Now, he posited in 1948 that the next 2 centuries would be dedicated to solving problems of organized complexity, and that with increasing computing power, we would now have the tools to try and explore some of these systems. So this was Weaver's classification. It was quite prescient in the sense that we do find ourselves in 2019 with a lot of work with the emergence of data science, etc., a lot of work on trying to understand systems like these, and these are largely prevalent in the social world, in the biological world, away from the more traditional applications of maths, which has been in physics. So just, from those examples, and we touched upon all of these things, is that now complex systems are comprised of, a large number of particles or objects interacting with one another. Now, what are the characteristics of these particles or objects? One thing that we see, and this is not like all of these have to be satisfied for it to be a complex system. This is sort of, some of these will be satisfied in general for a complex system. In many cases, you see that you're interested in behaviors of system as time evolves. So, and the one interesting thing that you see in these systems is that the objects or the agents of the system are often responding to what's happening in the system. So they are adapting to changes in their immediate environment, changes in the global environment. And, so this is, in many cases, an essential part of, complex systems. So if you think about, finance and, how people behave in the market, if you were to think of something like the herd mentality, it's very much a response over time to behavior of other people, to what's happening near you in the system, and your sense of what's happening in the larger system. So this is a critical dimension of how we think about complex systems. Connectedness. In all of these, or most of these systems, there are connections that exist between parts of the system. Behavior of if we are all participants in a particular system, my behavior is dependent on say perhaps behavior of those around me in the physical space around me. Depending on what the context of the system is, there is a lot of interdependency between the behaviors of all the agents involved. And diversity. Diversity is just to say that systems might consist of many different kinds of objects or participants. So if you think of social systems especially, there might be individuals, there might be institutions. The thing is that there are many different kinds of phenomena where you observe an outcome, and that outcome is not easily trackable back to an individual agent's behavior. And we'll go into examples of this because I feel that we should explore this in some specificity. But the idea is that once you know the emergent behavior of a system, your knowledge of the underlying agents and their interactions becomes, it's almost irrelevant as to what those things are. As long as there is emergent phenomena that you can measure, track in a statistical sense. So I will speak speak about emergence a little bit more in some detail as we talk about maybe 2 or 3 examples in some detail. Now, the first model of complexity in the social sciences was in the work of Thomas Schelling. Now, Schelling was a game theorist and a mathematician, and what he was trying to, explore was this phenomenon of segregation in American cities. Why is it that we were finding black and white Americans living in strictly segregated neighborhoods? Now, some of it is, of course, historical, but even after time had passed, you found that cities in America remain extremely segregated. And he was trying to explore this using, simple models. So what he did was to say, let us consider a two-dimensional space. So if you look at this floor, for instance, where each, square on the floor is a household or an individual. Now, individuals are of 2 types in his original model. In this, we have red and blue in this figure. So these are 2 kinds of individuals. And what he said was each individual has one characteristic, which is their tolerance level. It's what he called it. Now, a tolerance level is defined as what proportion of your neighbors are you willing to have that are unlike you, right? So if you're red, what proportion of your neighbors are you willing to have that are blue? And based on that, if you're unsatisfied, say you have a proportion, say 50%. I want 50% of my neighbors, I can tolerate 50% of my neighbors being blue. Then, if that number is more, then, I will move to another location where my condition is satisfied. If that number is less, I'm satisfied with my current location. If you were to run the dynamics of this, so if you were to fill the space randomly, if you were to, sprinkle reds and blues in a random manner, you would get some, configuration like this. So here, about 15% of the population is red, 85% is blue. So the red is, somewhat scattered somewhere in this. And you ran the model based on the simple rule that I will move from my current location if I'm unsatisfied with the proportion of blue neighbors or red neighbors, as the case may be, or I will stay there if I'm satisfied. And you let everyone make that choice in the model. That's the way he did it. So everyone got a chance to make the choice at each time frame. Very quickly, the model settles into some sort of a more structured equilibrium, where you have these blocks of red and blocks of blue. So you can see that from what was a fairly mixed starting point or initial configuration, you ended up with a very segregated final configuration. And the interesting thing, this you would expect, given the rule that we set, it's not surprising that people arrange themselves in this manner. But the interesting thing that that was critical, or the insight that he had, was that even if you had very high tolerance levels, you found that this was the outcome. So even if I was happy to have 2/3 of my neighbors to be of the opposite type, I would still end up with a segregated outcome. So basically, that suggests that, or it suggested that there was this disconnect between, the micro motive of the individual, which is to say that I'm happy to live in an integrated neighborhood, and the macro outcome, which was segregation. So therefore, which is the point I was trying to make in saying that this is an emergent phenomenon. Now, knowledge of this emergent phenomenon tells you nothing about how, tolerant the individuals in that neighborhood or in that city are. So emergence essentially means that a collection of agents is not just a collection of individuals is not just a collection of individuals making decisions. It is something more than that. It transforms into something more. And those are the kinds of outcomes that we see here. So his challenge then was to say that knowing the individual psychologies of everyone that lives in a city, or knowing individual preferences, was of no value in talking about. It is of value in the sense that if you have very high tolerance, I think over 70%, then you found that segregation doesn't happen. But up until that point, segregation was an outcome irrespective of how tolerant you were. And so this sort of started a lot of work around this notion of differentiating between micro motives and macro behavior. And it's interesting to look at this from the perspective of the history of science, because this kind of model of moving from, this kind of a transition from one sort of phase to another has a long history in physics as well, where they were studying physical systems, where phase transition was, was one of the founding, aspects of thermodynamics, for instance. That at 0 degrees you would have ice, and at greater than that it would be water. So there was that very, very clear phase transition. So in physics they've been thinking about in that context, but this sort of behavior being observed in the social world as well came about completely independently. They did not take that understanding from physics. This was purely work done by game theorists and mathematicians in trying to understand why segregation occurs. And so this is a robust phenomenon. Now they have tried this model across all sorts of definitions of neighborhoods, and changing the geometry, and removing geometry, modeling it as a network. The outcome is robust, and they've applied it to real data around the world and found that that the model holds. So again, it's a very simple model, and I think this is super important, that in creating these models you want to be very careful of what you put in. You don't want to overdetermine the outcome, in the sense that the input that you give should not dictate what the outcome should be. The outcome should emerge as as something that you cannot even imagine when you given the set of inputs that you have. And I feel that in creating these models, especially now, one of the challenges is because we have computational power, there is a tendency to define these models in very, very rich ways. So taking in lots of inputs, for instance, to create very, very precise, specific phenomenon. Now you create very rich phenomenon, but the model doesn't offer you anything in terms of an explanation. So in this model, it tells me the clear insight is that your motive is irrelevant to the outcome in the city, outcome of how neighborhoods shape up in the city. The problem with adding more and more into your model description is that you lose the ability to understand what is driving behavior. So one of the challenges with these kinds of models is, or one of the things to be wary about, is to be very parsimonious in your choice of the inputs that go into these models. Now, this kind of model is called a threshold model. Threshold models have been used for a number of things now to describe how riots happen. That riots are an emergent phenomenon. It's not that a number of people gather to conduct violence. It is that the interactions and the propensity for violence of some can very quickly transition into large-scale violence. So you need a very different way of understanding that than going into the details of who comprises your crowd. It's almost an irrelevance as to who comprises it. The thing is that there is an emergent phenomenon that's happening that is not describable by the underlying properties or the properties of the underlying components of the system. And I think that is the essence of emergence. And emergence is sort of the constant theme across all complex systems, is that you get emergent behavior which is statistical in nature. So for instance, I mentioned here that the system reaches a statistical or a dynamic equilibrium, which is to say that you run this model over time, starting with any configuration you want, you'll end up with something like this. But this doesn't mean that this is a static configuration. I run it for a longer period of time, agents will move here and there. It has reached a statistical equilibrium, which is to say that if I use a measure to try and define segregation here, that measure is consistent beyond a certain point. And that is what we call a dynamic equilibrium. Is that over time, the system will continue to evolve, but the property or the statistical property of the system that you're interested in stops changing. Now, this is kind of, I've done some work taking, this model forward. One of the, I was very interested in exploring wealth segregation. So this is, some attribute-based segregation, whether it's caste or race or binary attribute. In wealth-based segregation also, what you see, so this multiple colors are just, a continuous distribution of wealth. So the light colors are low wealth and the dark colors are high wealth. Again, you let, agents, so here agents are able to move into neighborhoods that they can afford only. So, you have to be able to afford the neighborhood that you want to move into. You always want to move into a richer neighborhood, but you have to be able to afford it. And if agents move based on that heuristic, you end up with a segregated outcome where, you see these dark patches where the rich have congregated. So you see, and so the same model, of course, you use the Schelling model. The question I was interested in exploring was to say, given that this is a fairly robust outcome, as a public policy maker, how would you think about reversing something like this? Are there mechanisms that that policy can put in place where we can prevent something like this? Now, one of the challenges is, and it's obvious once we've sort of talked about this so much, is that this is a dynamic phenomenon, and that any response to these kinds of configurations has to be dynamic in nature. In a sense, you have to track configurations over time. So one of the things that is obvious is that you don't want solutions that situate you in place. So for instance, if you were to build housing, say, so to prevent segregation, you go into a neighborhood, you build housing for the poor, and you move the poor in there. Now, at a static point, of course, that reduces segregation because you move the poor into a rich neighborhood. But the problem is that this is a dynamic thing. The rich move out. Then what do? You've created a ghetto of the poor. So, when we think about policy outcomes for stuff like this, it's obvious that you want policies that are tracking this outcome, that dynamically allow you to adjust. Where are the neighborhoods where, where the rich are congregating? What can I do? So, more rental or more, vouchers, things that people can use to move in the city. Movement is essential because the moment you make it static, one set of people are unable to move. And you've just moved the problem down the line. And what you need is a much more dynamic set of solutions to this. The other interesting thing, that I found in a very structured model like this, which was to say, using a lattice, two-dimensional, is that there's a very nonlinear effect of this, is that you don't need to allow all poor people to move into rich areas for this to happen. Remember that, people are constantly responding to, everything that's happening around them. And so what we found, for instance, was that even if you allow 2 to 3% of agents to move into neighborhoods that they cannot afford, you find an essential decrease in segregation. So if you were to enable something like that consistently, then, from a theoretical perspective, you would be able to, tackle a problem like this. But this, of course, is a theoretical, highly systematic result, and it needs empirical validation. But it was an interesting result, nonetheless, to say that there is, again, a nonlinear effect here. That, you don't need to move 50% of the poor into the rich neighborhoods and suddenly you have a mixed thing. You need to move 6%, 3%, some number like that, where you can see, because of decisions that others make, that you quickly see a transformation to a desegregated state. So what this offers, I would argue, is even if not, concrete policy proposals for what you should do, I think it definitely offers thought on what you should not do. And building, social housing or project housing, as has been done in many parts of the world, and then moaning 20 years later that we have ghettoized the poor, is it seems like a pretty obvious outcome from this kind of model, that you want to avoid doing that. Now, how you want to create a more dynamic set of incentives is a separate question, and maybe, you need more work before we get into, talking about what those policy prescriptions might be. But maybe not building for the long term is a good idea. Ownership, maybe not such a great idea. Okay, this is another, we talked about evolutionary models. I mean, we talked about the evolutionary timeline a little bit, where I was telling you that we see these, we see this kind of intermittent behavior, long periods of evolutionary stability, followed by short periods of dramatic change, and then following them again long periods. So the question was that is this just an artifact of the way life has evolved on Earth, or is there something more fundamental to this? Now, evolutionary models are fairly simple to describe. I mean, there is, of course, an underlying, to all of these there's an underlying maths to it, which is again not very difficult, but I'm not going to get into it. Anyone is interested, I'm happy to talk about it later. So if you think about evolution, right? So individuals, you have individual animals that are parts of that, so you have genotypes. So again, if you think of, all possible types of genotypes. So a genotype represents the expression of the DNA of an organism, right? And if you think of the genotype as a space, right, where some genotypes are occupied, meaning those animals or those birds exist, and some genotypes are potential, that, mutations can occur, and, you have the creation of that genotype. So if you can imagine that as a space, as a matrix, then, you have a random number of spaces occupied by species that currently exist. Now, in an evolutionary model, what you have is three things happening. You have reproduction, you have mutation, and you have annihilation. That's all that happens in the evolutionary model. Now, individuals. How do so when we say reproduction, as I say here, it's a function of the interaction between species and the environmental carrying capacity. Now, I should mention this is a model that came out of the lab that I used to work in, and it's something that we've tried to apply. I mean, started as trying to explain this intermittent behavior in the evolutionary timeline, but we have tried now to use it across a range of applications, like evolution of industries in an economy, trying to think about evolution of sustainability indicators for cities, for a number of such outcomes. And really, this is a way to think about any system that evolves. And one of the things that I was just talking to some of the folks at Dwara Research was that if we were to think about finance and the change, for instance, in the financial well-being of the household over time as an evolutionary process, then, can we think of modeling it in this way and what that might tell us? Anyhow, we can get to that, but in this case, so, you have these individuals representing certain genotypes present in that genotype space, and now these individuals interact with one another. Now, there are four kinds of interactions that were described in the model: predator-prey, then you have parasite-host, and then you have collaborative and antagonistic. So, this is the kind of interactions that exist, that can be there between two species. And this is just an example of, two scenarios. So, for instance, you have a banana, the banana, the monkey, and the lion. Now, in that case, in the left, the monkey is kind of concerned because there's very few bananas and there's lots of lions. So, it's not great from the monkey's perspective. Whereas in this case, much happier, because lots of bananas, very few lions. So the probability of survival is that much higher. So the point of this is very simple, to say that your success depends upon, who you're with. And in a sense, the really nice thing, or the thing that I really liked about this model, was that this notion of fitness that you often hear about, that species or animals have fitness, and that's why they're able to survive over long periods of time, is not something that's input into the model. We don't assume any fitness, anything of the sort. We only assume interactions. Now, interactions can be any of those 4 things, and that's random. So, you let individuals reproduce based on, this. The environmental carrying capacity is simply to say that the environment has a finite set of resources that it offers, and that all animals are competing for this, or all species are competing for this. So that's the carrying capacity of the overall environment. Mutation is just, as reproduction occurs, in some cases there are random mutations, and that's a random phenomenon. And annihilation is just to say death, that animals die and are born. So it's a fairly simple set of, actions that happen here, these 3. And when you run the model, with just that happening, we have not input fitness, we have not input anything about, how evolution will occur over long periods of time. It's just these 3 functions that are put in the model. What we observe, this is the outcome actually. This is the outcome of the theoretical model, which, if you remember the first slide, is sort of is able to capture that kind of behavior where you see consistency in species over long periods of time, followed by short bursts of great volatility in the genotype space. And the interesting thing is that this notion of selection or adaptation is happening at the level of the overall space, at the overall genotype space. So what we found was that fitness is useful here as a description of the overall environment, not as at the level of an individual species or a genotype. That, these states are stable because they are high fitness states overall. That they're able to support so much life over long periods of time, whereas these states are low fitness states because they're not able to do that. So the fitness becomes a property of the ecosystem, not of an individual species. Now, fitness is a very problematic concept. There is no agreement of this in biology, and unfortunately, this is the kind of concept that is being taken into society. It's being used in bad ways. I mean, if you just look back at World War II, it was all about, this kind of a notion of natural selection and fitness. I thought this was a nice way of thinking about fitness as an emergent property, that you're not fit in and of yourself. I mean, that's sort of a meaningless thing, that you're fit because of your interactions with the environment. And that is sort of, it sort of feeds back and forth. That, everybody is fit because you're there, you're fit because this equilibrium is there. The moment that changes, then that whole ecosystem is unfit, or, of low fitness. So it's a nice way of saying that fitness is an emergent property, and that you could actually generate the evolutionary timeline with these evolutionary stable states and those intermittencies that were observed in the actual fossil record. So this is actually a very interesting model, and one of the things that I want to explore a little bit, and maybe we can talk about this, is if you were to think about finance, and this is what we all here think about, we worry about in many different contexts, whether it's markets, households. Are there ways in which these tools can be applied to better understand the systems that we are a part of? Now, so finally, talking about finance, I mentioned the 2008 crisis, and it was a very useful point where we started talking about how we think about finance. How do we think about markets? Because a lot of this was given the efficient market hypothesis, and this is how people ought to behave, and there had been a lot of success, or there had been a lot of presumed success in the financial industry, at least to say that finance had enabled a lot. And in some sense that is true. Finance has enabled a lot over the last 60 years. But what we saw in 2008 was that there was a lot of hidden risk in that system that we simply did not know existed, and therefore our models were either bad models, in the sense that you use bad assumptions. Even if the see, one of the problems with models is the maths might look good because the maths is just, you know, one step to another step to another step. But if your underlying assumptions are bad, you know, it's built on a foundation of nothing. So, you know, one of the things we were left with was, you know, what is happening? Why did we miss something as big as this? You know, we thought, I think at least in the West, I remember the sense was that post the Great Depression, that we had learned a lot about, you know, what can go wrong in a financial system, and we had sort of plugged those things, and now we were having sort of a second, you know, Great Depression or Great Recession or whatever it's called. And that time, I think it was a bad time, but I think in a sense, it also saw the emergence of multiple other ways of thinking about finance and the way people interact with the financial system. Now, one of those approaches, this came a little bit before the crisis, was the adaptive market hypothesis. Now, one response that has actually gained a lot of ground over the past decade is this notion of behavioral economics, and with Thaler's, you know, Nobel, there is a lot of interest in trying to explore our financial behavior through the lens of, you know, this economics of behavior, and it you know, it talks about a number of cognitive limitations that we have or biases that we have, and you know, so it's generated a lot of literature on this front. Efficient markets hypothesis, of course, is classic, you know, financial markets theory where you assume one rational behavior, and you know, and from that you get a set of, you know, outcomes for the market. Now, clearly, that was not the case. 2007 proved it. The adaptive markets hypothesis was an attempt to reconcile, you know, the insights from behavioral economics with the more classic model, proposing that, you know, we study the financial system as an evolutionary system, where there is, you know, competition, adaptation, and natural selection. So the kind of model that I just talked about, where you have, you know, a number of diverse participants in the financial system who are interacting with one another. They are constantly adapting to decisions made by other people. And the outcomes of this model clearly suggested that the fat tails that we saw in 2007 were actually reproduced using the theory. So clearly, you know, there had been limitations in the way we had thought about finance. And complex systems certainly offer us an alternative way, a more, I would say, holistic way of trying to get at what might be driving certain kinds of outcomes. But I guess my prime interest is in talking about the core of what Dwara does, which is, you know, financial service delivery at the level of the household, at the level of the enterprise, or, you know, even dealing with, you know, large number of enterprises at the same time. I mean, the work of both Northern Arc and Dwara KGFS, I feel, offers, at least in a preliminary, speculative way, applications for complex systems type thinking. Now, one thought I had, and again, these are all very, you know, balloons in the air. I haven't really thought about it in great depth, but I feel require, you know, offer at least points of departure from the ways that we normally do things. One is, you know, how is a financial service delivered to a customer? When you think of KGFS, one of the things that has been talked about over the last 10 years is that finance is synthesized when the needs of the household, the situation of the household meets the provider. So what we are essentially saying is that you have a customer with a set of needs, with a given situation at a given point in time, meeting a provider. Now, what does the provider bring? You can say the provider brings credit and insurance and all of that, but I think it's useful to say the provider brings certain capabilities. And if we go back to, you know, I think it was Merton's work, where he said finance does three things. It enables transfer of resources through space, time, and states of the world. So what the provider brings is these three abilities, and different providers bring it in different ways. And what you when these come together, you're producing a basket of products for the customer. So in some sense, that can be thought of as an emergent outcome of that set of interactions. And this ties in, and this then goes to the question of what happens when a customer or a household takes a set of products. You've determined that, this is a set of products that makes sense given the situations. What we also know, and this has been brought home over the last 10 years quite dramatically, is that things change over time. That a set of products that was great for you at a given time based on your needs might not be the same set that are relevant to you 5 years down the line. I mean, your situation has changed, perhaps. The market around you has changed. The institutions have changed. Technology has changed. Is there a way in which we can study this as a system that evolves over time? Now, this is just, as I said, thinking out loud and, merits perhaps more deeper thought. Maybe it is, maybe it's not. But I feel that, it definitely offers a rich space for exploration. And finally, this notion of suitability and unsuitability. As a provider, we are often concerned that, we must or we ought to be offering products and services that are suitable to the customer, given what we know about the customer. And I think that's very important because as a provider, you want to be doing that. The only thing is you need to be able to track, to dynamically change some of these things over time. And we can maybe explore directions that research can take on that. But from a policy perspective, how do we think about suitability? One of the things in all these systems that we saw, whether it's evolution, whether it's markets, whether it's cities, these are like dense systems, right? Lots of, components, lots of interactions that we really don't know what the nature of those interactions are. We don't understand the specifics of the interactions. What we understand are higher level phenomena. Given that, how do you intervene in such a system? How should we think about intervening in the financial system? Is there a way we shouldn't intervene in the financial system, for instance? I would just argue that, given the scale and the scope of these systems, their reach and their ability to affect millions of people, that caution, and I've just put the precautionary principle, which is just to say that in large systems, I think the first step to take is precaution, that you don't want to hurt the system. Because intervening in a big way can lead to unintended consequences, and by that I mean all consequences, because we do not understand almost any of these systems with the level of precision required for big interventions, and what they will cost. Demonetization is a great example, where we went big intervention, and well, that most people would have said you should not have done it. But even if there were two, ways of thinking about it, from a complex systems perspective, I would argue that it's not a great way, simply because we don't know the consequences of what will happen when we intervene in such a massive way in the system. You always want to intervene at the margins. You want to give space for evolution to occur, because those are the ways in which we can control, what happens here. Otherwise, it's quite dangerous to go in and try and do stuff that we don't know what will happen. Which is why I would argue that when we think of suitability, from a provider's perspective, it's a great idea. But from a regulator or a policymaker's perspective, probably unsuitability is a better idea. What is it that you want to prevent? What are just bad ideas? So, for instance, the work that you guys had done on microcredit and unsuitability. Now, there are ideas there that perhaps a regulator can take and say that, I might regulate on X, Y, and Z because this is bad for everyone. That, I don't want to allow these things. There might be a more reasonable way to intervene than coming in and trying to regulate on what is suitable. That is probably a decision best left between buyers and sellers of products than for someone dealing at the system level to come and impose in any way. And this was just as a more general principle of dealing with interventions in large systems. I talked about the segregation, where a big intervention is going and building, because that's a lot of money, public resources, and over time, you can say it's an unintended consequence. But, if we had done some of this work before, we would have seen that this consequence is inevitable. It's just because we don't know that consequence will happen, we sort of, intervene in some of these ways that we perhaps shouldn't be. In any case, I feel that is kind of, what I wanted to say. I wanted this to be a sort of a very broad, brief introduction to complex systems. This is sort of a very rich field of inquiry, as I was saying, more predominantly now in the social and the biological sciences than even the physical sciences. And I feel that even in the financial system, in the kind of work that Dwara does, there might be scope for looking at some of the questions that worry us through the lens of, of complex systems. So thank you very much for listening. I really appreciate your time. Happy to take questions.